Welcome, Chris Jermaine here. Chris comes from Florida. He is one of those decorated, recently tenured professors, right?
Going through the tenure process. Not quite there yet.
Sloan Fellowship, NSF career, everything an assistant professor ever dreams of. And the best paper award at Sigma last year, which is blows my mind away. So with that introduction.
Well, thanks. Nice introduction. Well, thanks everyone for showing up. I guess I was warned that the group might be small, so this is actually great. Okay, so in general, I'm going to be talking about databases, okay? And I don't know how many of you actually have a background in databases, so I'll kind of aim this at a general computer science audience. So as a database person, I'd be one of the first to argue that databases are a key computer science success story. And some of us...
Let's have an argument. Let's get started.
Well, they are a key, not the key. Not the key. Notice that I didn't say that. And so some of us database people go as far as to claim that some or much of the 1990s economic boom was due to the wide deployment of relational database management systems. Even Alan Greenspan might agree with that, although people blame him for everything now, so maybe that's not a great endorsement. And so how can I come here and claim that database performance actually needs help, given all the successes that we've had? And my claim is actually that performance might be great for transaction processing, but it's not so hot for analytic processing. And so first off, I'll spend some time talking about what exactly analytic processing is. So analytic processing is big queries in databases where the queries and the databases are statistical in nature. And so here is actually an English version of one of, it's kind of a key benchmark query in something called the TPCH benchmark. Now, in case you don't know, the TPCH benchmark is, it's a benchmark or a set of database queries and an associated database that's put out by a consortium of hardware and software vendors. And so this is something where the database guys then go and they show how great they are by running their queries on this benchmark. And so here's an example of an AP or analytic processing query. So what you have here is something that's statistical. Okay, so you're asking for actually a sum over a numeric expression. And then you've got a from where you're listing several tables. So there's actually a join. And these tables are quite large, maybe not as large as what you guys have here at Google. But for database people, they're large. And then you have operations like group by and a sort over here.
What is large in this case?
Well, actually, that's a very good question. So I'll hit on that in a minute. But large, you know, the largest databases now are on the order of, say, hundreds of terabytes.
I mean for this benchmark.
What is...
So you said there's specific tables that are put out for this benchmark?
Yeah, well, actually, there's a data generator. Okay, and so what you do is, so the way that it works is that you architect a system. And you say, hey, I want to architect my system so it's going to work on 100 terabytes of data. And then you actually type in 100 terabytes and press return, and the data generator spits out 100 terabytes of synthetic data. So you actually see benchmark results published for anything from, say, 100 gigabytes up to around 100 terabytes. So that would be the range, kind of 3 orders of magnitude. But so as database people, we consider a petabyte to be huge, I think, and kind of within that order of magnitude is our limit.
I just was curious about the specific benchmark.
Okay. Okay, so this particular query is equivalent to the following. So what it says, given database tables, line item, orders, and customers. So for each group induced by the group by order key, order date, ship priority clause. And by the way, if you don't know what a group by clause does, well, it essentially applies a separate selection predicate to everything in this cross product. So you can imagine that we've got these 3 tables. And what we're doing is we're looking at all possible combinations of tuples or records from those tables. And then we're basically saying that we're going to break this up into groups based upon those subsets in the cross product that have the same value for order key, order date, and ship priority. And then for everything in that cross product, you basically compute the result of this function over the tuples in the cross product or the records in the cross product. And this f of LOC returns 0 if the where clause is false for a given LOC combination in the cross product. Otherwise, it returns the value of this aggregate function. And so basically, essentially what you're doing is you're doing nothing more than a big, huge nested loops computation, right? Okay, so that's analytic processing. Okay, so now here's the fun part. And the question is, so if this is the kind of query that we want to be able to answer, so the question is, how bad are current analytic processing solutions? Well, you can actually go online and look at the benchmark results. And it turns out that if you take a quick check of the recent TPCH results, what you find is that somebody can spend almost $1 million to store 300 gigabytes of data. And they actually do this in 17 terabytes of 36 gigabyte disks. And it turns out that one of the benchmarking queries still takes 18 minutes to answer in the throughput test in the TPCH benchmark. And the throughput test actually kind of tests a bunch of things concurrently. Now if you got 10 terabytes, so let's kick it up by a couple orders of magnitude. Well, it turns out you can spend almost $7 million, and then you're going to wait 4 hours for one of the queries to execute. Okay, so that's not good, I think, by any measure. And actually it's quite interesting in the sense that these companies actually proudly display these results. Okay, so they think that these things are great. And so my conclusion is that current analytic processing solutions are not there. They're not very good. And the result is that there's much frustration from the industrial user base. And people are actually starting to complain about this. So they're complaining that Oracle and IBM are not really solving their problems in this arena. And the result is that there are actually several recent data warehousing and AP startups out there that are really trying to compete in this space. Well, so actually I have a couple of students who just graduated and they're going to Greenplum. So that's actually here in Silicon Valley. Then you got like, so Stonebreaker is starting Vertica, and there are several companies in the Midwest that are starting that. Okay, so what I'm going to talk about, what I'm interested in doing is helping this out by actually applying the idea of approximation to this particular problem. And so my ideas, or my use of approximation in helping this bad performance, is based on 3 key observations. So number 1, analytic processing is almost always statistical. So if you're asking statistical queries where you got sums and averages and standard deviations and such, it's not clear that 1.3745 million always differs from 1.3757 million. Now, quite often these numbers are very different, right? There are certain queries where if you have an error out 4 places in the decimal, past the decimal, that's a big deal. But in a lot of applications, it's actually not a problem, right? And actually, a good argument for this is that, as Alon certainly knows, a lot of the data that gets into a warehouse is a result of a data cleaning process, which is inherently erroneous anyway. And so why are you actually spending all this time getting 4 digits of accuracy to get the wrong answer, right? And so this is key. This observation that maybe you don't need 4 digits of accuracy is key, because it's often the case that you can get something like 0.02% error a lot faster than you can get 0 error. So why do you spend all the time going for the 4 digits of accuracy when you don't need it? And so given that, I'd like you to imagine the following database management system. So in this system, you ask any AP-style query, and the system comes back and gives you an immediate guess. This guess is bracketed by a confidence region. And by confidence region, I mean something that is statistically valid and says that the answer is actually within these brackets. This confidence region should shrink throughout online and computation and be to 0 by the time you're done. So we got 0 with the query completion. And the total execution time, if somebody actually decides that they want to run this thing all the way to completion, should be exactly the same as it is for a classic RDBMS. So you should get this approximation with no extra cost. Okay, so that's kind of my vision. That's where I'd like to go. Okay, so any questions so far, by the way?
Do you have a definition for an AP-style query?
Well, no. I mean, there's not like a canonical definition, okay? So what I would say is that I can tell you what the characteristics are. That's the stuff that I kind of outlined before, okay? So it tends to not be very selective. It goes through a lot of tuples in this big, huge cross product. The answer is almost always statistical, right? Along with some grouping and kind of ordering and so on. Typically what you don't do, and what databases are actually very good at now, what you don't do is drill down to a specific record or subset of the records, right? You're talking maybe, say, 1/1,000,000th to 10% of all the records in a huge cross product are going to be useful. Okay, so it's big. It's a lot of the subset of the data. Other questions? Yeah.
Your confidence interval, is that an absolute, or is it like a 95% confidence interval?
Yeah, it's a statistical confidence interval. Okay. Yeah, I'll actually be talking about that in a lot more detail. Okay, anything else? Okay. So the question is, of course, hasn't this been done before? Well, people have actually been batting these ideas around for like actually almost 30 years now. And there's actually a very good example of some of the guys at Berkeley and IBM Almaden worked a lot on this problem. So they had this thing that they called the control project. And this was really what I think is the first kind of complete attempt to foray into this area. And these guys got the error guarantees. They got online computation for some queries. But what they didn't get is they didn't get complete execution from start to finish. They didn't get scalability, and they didn't get generality. And I would argue that because of these problems, this really never took off. So it's not clear to me that you're ever going to have a viable system that can only do this online aggregation or this approximation for a few seconds and then runs out of memory, right? I think that you've got to have something that you can basically plug in as a surrogate for Oracle or for DB2, not get any kind of hit in terms of the performance, and have it seamlessly work so the whole time you get your approximation, right? I think that you can't expect somebody to give up anything. You've got to give them everything they have now, but then give them a little extra. Okay, so our work. So our goal is actually more ambitious than what the control people did. So we actually want to redesign the database from the ground up based upon randomization and approximation as kind of the key design principles. So we still want to be able to do this and have scalability for exact answers. And this is actually challenging because randomization and fast computation of exact answers are often at odds, right? If you're randomly throwing stuff on a disk, then a lot of times you got problems, right, trying to locate it quickly. And the resulting system that we're in the middle of prototyping and evaluation is something called DBO. Okay, so how to do this? Well, given an implementation plan like this one, the question is, how are you ever going to guess the answer from start to finish? And again, since many of you are probably not database people, you might not have seen something like this. But this is like a graphical representation of something called a relational algebra expression. Okay? And what this is you can think of it as like a numerical algebra expression, except that it has operations that work on sets. And we've got here some of the key operations that you tend to find in an AP-style query. So you got something like a join right here. And so what a join does, it says find all S and S, T and T combos where there's some link, right? So a join might take two big tables and link pairs up where the, say, employee ID is the same. You got things like an anti-join operation where it actually says find, in this case, find all ST and S join T where there's no U and U, where ST.B equals U.C. In other words, it's basically subtracting the sets, okay? So you got a query plan that's pumping all this data through these operators. And somehow you want to look at everything that's going through the operators and be able to guess what the final answer is going to be. Okay, and so this actually seems pretty hard to do, I think, at first blush. And so my observation is that Haas and Hellerstein in 1999, these are the control people, they gave us something called the ripple join. And this actually works pretty well for this particular part, at least in very limited circumstances. So I'll start my examination there. Okay, so the ripple join, some of these basic ideas are really what our system is based upon. Okay? So what the ripple join does is it says, I'm going to start out by throwing the data on disk in a statistically random fashion. So both of the input tables in this case, we got two input tables, are going to be randomly permuted on disk. And these things might be very large, and so you can imagine that the way you would do this is by first associating a statistically, well something that's, say, pseudo-randomly generated with every single tuple, and then you do an external sort based upon these pseudo-random numbers that you glue to the tuple. So these guys are randomly placed on disk. And so what I'm going to do is I actually want to come up with a guess for what this answer is as I scan the data. Okay? Well, since the data are statistically random on disk, it turns out that if you simply do a sequential scan of emp and a sequential scan of sales, then all of the tuples or records that you've read so far are going to be a statistically random sample of all the tuples in both relations. And because of this, it turns out that there's a very nice unbiased estimator for the final answer to this query. All you do is you take a look at all the tuples you've read in so far. You actually compute exactly this query on that subset of the two input relations. And in this case, if you compute them, you get a 0. And the reason is that Jan and Tom don't match up. In this case, emp.a would be like the name of the person. Okay? And so this is A and this is A. They don't match up. So what we get here is we get a 0 on the subset of the data we read in so far. Right? Now, if you just took your 0, this would be biased for the final query result. So what you got to do is to unbias it by multiplying the 0 by the inverse of the sampling fraction from each relation. And so you actually get a 36 times 0, and it turns out that this 0 is unbiased for the final query result. And by the way, in case you don't know what unbiased means, it means that if you actually randomly shuffle these input tables an infinite number of times, reran this, and this process an infinite number of times on every single instance, then on average you would get exactly the right answer. Okay? Okay, so now the next thing that we do, it's a little hard to see on the screen, is we read in another tuple from each input relation, do the join, and now we actually get a hit, right? So you find the 3. So the 3 gets put in here. You scale it up by the inverse of the 2 sampling fractions, and we get 3 times 3 times 3, or 27 as a guess. Okay, now of course the guess has gotten a lot more accurate because its variance, or its inaccuracies, has now decreased. Okay, so you read in a couple more tuples. So we got Tom and Joe, and we got Sam and John. Now we've got 2 hits. So you take 3 plus 12, you multiply it by the inverse of the sampling fractions, you get a better guess. And so you keep on doing this, and eventually, once you've read in all the data, you get something that's equivalent to the final answer. Okay? So this process has a lot of nice properties. It's consistent, which in statistical terms means that as you get more and more data, the variance of the estimator is guaranteed to decrease. You can't do worse by having more information. Actually, it turns out that the error is normally distributed. There's a central limit theorem for this sort of thing. So it's got a lot of nice properties. Okay, so great thing. Because it's a really key invention in I would say even in the history of databases, at least in the last 20 years. So any questions on this?
So that's for a, there are all sorts of simple arithmetic or algebraic properties that if you take a sample of them, so if you 1 over some normally distributed estimate isn't going to be the estimate of 1 over the
Right.
true value, and I'm trying to convince myself that you're not going to build in that sort of bias with your estimates.
Yeah, so, okay, so you're right. So, yeah, I don't want to go too far down that path. Okay, let me just say that this is accurate for the simple case of a sum query versus some arbitrary expression. Okay, so you're talking about there's all kinds of theories behind ratio estimators.
Sure, ratios are the ones that come to mind.
Right, now ratios you actually get, it's actually possible to unbias, and actually the simple thing for a ratio estimator is actually asymptotically unbiased. It actually has it only has bias for very, very small sample size, but it turns out actually that the tricky thing in that case is you actually have to use like a delta method to get the variance and so on. So there's a lot of statistical issues associated with, let me just back up and say, you're right, and that gets very complicated very quickly, and it's beyond the scope of this talk. But catch me after and we can talk about it.
Okay, just want to make sure people are thinking about this. Okay.
Yeah. So
Great.
this is, I'm trying to keep it simple by saying we're doing a sum over some arbitrary function. In this case, everything I said is true.
Thank you.
Okay. So the issue with all this thing is, while it's great, okay, and you can actually extend it to other functions, although it's challenging, only the hashed version of the ripple join is practical. So what I mean by hashed is that the way you actually implement this is that when you read another tuple from AMP, you do 2 things. First thing you do is you probe a hash table for sales that stores all the hashed tuples from sales to find a match. If you find a match, you update your aggregate so far, right? Then you have to take that tuple that's just been probed and put it in its own hash table, right? Then you read another tuple from the other guy, probe over here, put it in its own hash table. And you keep on doing this back and forth, and it all works great until you actually run out of memory, right? And it turns out that this can happen in only a few seconds on reasonable hardware. So nowadays, you're probably talking about a 70 megabyte per second sequential scan rate, right? 5 disks. You know, you have a simple RAID with 5 disks, and now you're up to, was that 350 megs per second, right? And so in only a few seconds, you're going to overwhelm even a very large memory for a single machine. And so what this means is that your estimation process works for a few seconds and everything dies because you can't store these hash tables in memory. So the issue is that while this hash ripple join might not be directly applicable to our particular problem, the idea of always adding more and more randomized data and looking for lucky result tuples, so these kind of hits that will actually contribute to the final aggregate, is central to query processing in our system. Okay. So first of all, is everyone clear what the problem is, right? You got to have some way to do this probing back and forth, and as soon as you have to page these things to disk, you're going to be in big trouble. Okay, so that being said, so how does DBO deal with this? Okay, well, imagine that we have a really complex query plan. So in this case, we have something that looks like an 8-way join, okay, on just 8 arbitrary tables. And by the way, I'll assume for the time being we have a bushy query plan and not something that's deep, like with a spine to the left or the right. Okay, so what happens in our system that we're working on is that first, all of the bottom level table scans are processed concurrently. So all of these table scans, they start reading data from disk, and this concurrent processing of the table scans is called a level-wise step. Okay, so the first level-wise step at all times checks for lucky answered tuples. So what I mean by that is that as the data are flowing through these table scans, the table scans are essentially chattering back and forth and telling each other what they have, what they've seen. And so if they happen to get lucky and find an output tuple that actually is going to satisfy the where clause of the query and contribute to the aggregate, then this, or actually if they don't get lucky, if they get lucky or not get lucky, this actually allows you to come up with a guess, actually an unbiased guess for the final query result. And so the way that we characterize this is as a random variable, which we'll call n1. And it's 1 because it's the first level-wise step. Okay? So our guess is going to be characterized as a random variable. On expectation, the value of the random variable is exactly the query result, but there is some variance or error.
Sorry, to make it clear. So this is the random variable associated with the final question, query,
Yes.
aggregate query, or is it one for each separate random variable for each of the sub-queries at the level 1?
Okay, good question. Yeah, so what it is it's a random variable that corresponds to the guess produced by each of these individual table scans chattering back and forth. But it's a random variable that on expectation is actually equal to the final query result. Okay? And the reason is, kind of intuitively, the reason you can do that is that at some point, everything that's going to flow through the top of this query plan has to come from right here, right? And so if you kind of get lucky and happen to run into those things as you're doing the table scans, you can imagine that it's possible to make a guess for what the final answer will be.
So I guess the reason I'm a little bit confused is because you sure have the joints, but we don't know in that schematic what is actually going to flow to be counted to the top.
Yes.
You know, is it going to be something out of B or, but so there's something I'm missing here, so maybe I'm...
Okay, well let's back up and kind of, again, talk about what an SQL query does, okay, or what a database query does. Effectively, okay, at least in the case of something where you don't have like an anti-join or subtraction, what you do is you can imagine doing a cross product, an 8-way cross product, okay, of all these things. Then everything that comes out of that cross product, you feed it through a Boolean selection predicate that either accepts or rejects the tuple, okay? And then you take the result of that and feed it through a final aggregate function that maybe computes your total revenue or something, okay? And so what's going to happen is that, again, each of these guys are flowing eventually through cross products. I mean, that's what you can think of these things as doing. And so it turns out that at every single tuple that's going to come up through the top has to have its constituent parts come through the table scans, right? And so if I ever see that in memory I get lucky and all the constituent parts for a given tuple are in this black box at the same time, right? Then I have a tuple that's actually going to contribute to this sum up here, okay? And by seeing those things or not seeing them, it allows me to come up with this random variable n1. Yeah.
So each table scan is not only, A's table scan is not only talking to B, but they have a global picture of what's happening.
Yeah, exactly.
Okay.
Yes. Okay. Okay, so yeah, so this current value of the guess corresponds to a random variable, and the use of this n1 plus an estimate of the variance of n1, plus a central limit theorem over these kinds of cross products actually gives us statistical bounds. Okay, central limit theorem actually applies in this case, and it says that the error is normally distributed. Okay, so eventually this level-wise step completes, and all of the lowest, so all of these lowest joins are done with, and n1 is frozen. Okay. So at this point, what you've done is you've actually run the joins, the table scans are completed, they've fed all their data into the joins. And now we've actually materialized, or at least we don't actually have to materialize them, but you can think of materializing these things. All of these intermediate tables are now sitting there somewhere, okay? And so we're partially done with evaluating the query plan, and we've got this guess. Now the guess could have possibly seen all of the tuples because it's seen all the data that went into them. But because the timing could be off and you didn't happen to get really lucky and see everything at the right time, of course you're going to miss a lot of stuff, okay? So while n1 is now frozen, it will not be updated because its particular set of table scans or its level-wise step is done. It still has some inaccuracy, okay? So what do? Well, not surprisingly, you recursively do the same thing. So level-wise step 2 begins. And this level-wise step has its own estimator called n2. Now, it's not good initially because n2 hasn't seen much data when it first fires up. but it soon becomes far more accurate than N1. And the reason is that you can think that the A and the B have kind of been condensed into AB, and so the density of information there is greater. Okay? So the likelihood of seeing any particular result tuple gets a lot higher in this step. So while initially you haven't seen much data and N2 stinks, very quickly it has far more accuracy than N1 because it's seen a lot more data that's relevant to this guy up here. Okay, so the thing is we want to use both. And so what we do is we actually create this N, which is nothing more than a weighted sum of these two N1s and N2s. And it turns out that it's very easy to argue mathematically that by doing a very simple optimization problem, by putting them together, you get an estimate whose variance is lower than either of the constituent parts. And so, yeah, so we have this N, and this is actually what's displayed to the user. And it gets better because it's got more information. Okay, so not surprisingly, eventually this level-wise step finishes, and N2 is frozen as well. Now at this point, we're going to fire up yet another one of these things. Right, so you fire up another one, you now get an N3. In this case, level-wise step 3 begins, and in general, you're going to incorporate this new guy in here via a simple optimization problem. And N is, again, continuously getting updated and given to the user. Okay, then level-wise step 4 fires up after you're down to one last table, right? And this thing actually gets piped through this guy directly. And eventually, the variance of this N4 is going to go to 0. And the reason for that is that eventually, every single result tuple has been piped through the aggregate function. There is no correcting for bias, right? There's no sense in which you could have ever missed anything. So eventually the variance of N4 goes to 0, and then the weighted sum has to go to 0 as well. Okay? So this is a very high level how DBO works to give these guesses from startup through completion. Okay? So any high level questions on this? Does that make sense?
So the weights fixed, or how do the weights change, or?
Yeah, so it actually turns out there's a very simple Lagrangian optimization that goes on here, okay? So what you do is you basically just choose the weights so as to minimize the overall variance, okay? And so continuously before you send an update to the user, you recalculate the weights based upon the variance estimates for each of the N1 through N4, update those weights, and then that updates the estimate, okay? Because like eventually, right, so let's say right when N4 starts up, or the fourth level step starts up, N4 has seen no data, so it's got high variance. But very quickly, its variance shrinks. And so the weights adapt to that.
So the weights are computed based on initial sizes of A, B, C, D up to H, or on the query specifics, or a combination of some manual
yeah, good question. So they're updated off of an unbiased estimate for the variance of N1 through N4, okay? And that itself is an extremely complicated thing to deal with. Estimating the variance, so actually if you're, yeah, so you basically just kind of trust me that we come up with a statistically unbiased estimate for the variance, and that's what goes into this optimization problem.
So bottom line, the weights change as the query is processing?
Yes.
Towards the end, N4 will have weight 1 and the rest will have 0 in the beginning.
Yeah.
The rest will have.
Right. And the engine that powers all of this in the end is actually coming up with some kind of estimate or a statistical characterization of the process that allows you to get an estimate for the variance. Okay.
And one last question before I drop off this. The initial estimates for the weights is based on the query or the data or combinations of them?
It's actually based upon the weights are always based upon the variance estimates, which themselves are based upon the data.
Only on the data, not on the query.
Well, actually, I don't want to say that. So it's actually, yeah, it's based upon the data and the query, those two things. Okay, so properties of the query actually, so in the end, right, you can imagine there's some huge, nasty, gnarly recursive formula for the variance, okay? And then we have even huger, nastier recursive formulas that estimate the variance based upon what we've seen so far. And these things actually have as a component the data, and they actually have as a component properties of the query. Okay, so I think your intuition is correct there. Okay? Okay, so details on this. Okay, so there are several key system design changes here compared to a classic relational system. And by the way, is there a clock around? Oh, there we go. Okay. So in DBO, okay, so all these relational operations have to communicate, right? They're always searching for lucky result tuples. And so in a classic relational database system, you think of these things as being basically black boxes. A join does its own thing. It has no interaction with the outside world, except for the fact that it's probably competing with resources. Okay, but here in DBO, they're actually doing a lot more than competing for resources. They actually participate in a carefully choreographed dance that I'll be talking about. And another key thing is that we always need a semi-randomized output from all the relational operations, because if you don't have some sort of randomized output, it's impossible to statistically characterize what's going on. You can't argue for unbiasedness. You can't say here's what the variance is if you can't statistically characterize the order in which things come out. And the easiest thing to characterize is to say, hey, this thing's random or at least semi-random. Okay, and so of course we need lots of analysis, and I'll skip over this today. And the thing that I'll focus on is this whole process, which I think is pretty interesting, of how all these operations actually communicate so that DBO looks for these lucky result tuples. Okay, so basic data flow in DBO. Okay, so here's a simpler query plan. So you can imagine that we've got table scans that are operating over A, B, C, and D. So there's a set of pipelines that are bolded here. And in a level-wise step, the data flow between table scans or relational joins through these pipelines. Okay? So the brain of DBO is a software component called a controller. And what it does is it blocks and taps these pipelines, where tap is basically a forking operation that carries copies of the tuples coming through each pipe into this other software component here called the in-memory join. Okay? So the brain, the controller, is responsible for putting blockages in the pipes. Okay, so what it does is the controller, by unblocking one of these pipes for a moment, it allows a tuple or multiple tuples to flow through the pipe. One copy goes to the in-memory join, and the next copy goes to the relational operation. Okay, so basically you can imagine the controller is just basically pulling these levers, right, for all these things that are allowing tuples to flow through here. Okay? So to actually facilitate randomization in this process, all of the tuples from relational op are supplied in order of a random value from 0 to 1 that is associated with each tuple. Okay, this is what we just call this for no reason a timestamp. Okay, so in this case, let's say that we've got relation A, and it's got two attributes, A.A and A.B. So what we do is we somehow associate a timestamp with each of these tuples. And conceptually, you can think of the following process. What you do is you stamp a timestamp with the tuple, then sort all the tuples based upon their timestamp. This is at least logically what's happening. And then these guys are sitting there ordered based upon their timestamps. Okay, so now you got all these guys sitting here sorted on their timestamp, A, B, C, and D. So what happens is that the controller looks at all these timestamps, and it chooses the guy with the smallest timestamp, and it pulls the lever to unblock this thing. So the guy with the smallest timestamp, the 0.04, comes through, it flows through into the in-memory join. Okay. Next, then, the controller looks at this one, unblocks that guy, unblocks that guy, unblocks that guy, keeps doing this, and so on. So that's how it sends things through. Okay? So what the in-memory join is seeing is basically seeing something that looks a lot like a global randomized order of all these tuples. Okay? So that, of course, begs the question of what's happening inside the in-memory join. So the controller is directing copies of these guys to the in-memory join. So the job of the IMJ is to look for these lucky combos of tuples that are going to satisfy a where clause and to use this to estimate an aggregate. So for a simple example, say we're trying to answer sum over R4.G, where G is just some attribute. Okay? And we've got a where clause that effectively just links relation 1 with relation 2 with relation 3, relation 3, and relation 4. Okay, so you can think there's a chain of links. So an example in the real world might be that you have employees, you have sales, and you have supervisors. Okay? And so you're basically saying that I want to know, say, the sum over all employees who've been supervised by someone in this particular division of the company. Okay? So you've got to link employee with their supervisor, then you've got to link the employee with the sales that they've made, and then an aggregate over all those links is going to give you a query result. That's exactly what we're modeling here. Okay, so, was there a question?
So, either I'm just catching up, or maybe I'm stepping ahead. I'm not sure which it is. So, at any given point, you have a set of in the in-memory join. You have a set of tuples for all of the variables that you're concerned with, and you can see, does this satisfy whatever properties? Then you get a tuple at random that knocks out one of those tuples, and this is presumably another random sample, which in some ways is not independent, but in the aggregate somehow can, you can basically use this, when you get the next A in, it knocks this A out. That's, you now have another full set of tuples, and in-memory join just builds on that.
Yeah, I mean, I think actually you're stepping ahead, so that's exactly the kind of stuff I'll talk about. So, yeah, so you can, so you're anticipating exactly what I'm going to talk about. So, in a few minutes, ask that question again, okay? So that's actually great, at least it shows I set this up correctly, okay? So to deal with this particular query, okay, the in-memory join would have 3 hash tables to actually implement this. It would implement this by having 3 hash tables and 1 list, where the list is a list of discovered aggregate values. Okay, so what I've got is I've got a hash table for R1, R2, and R3, right? So the black circles there show what I'm hashing on, and then I've actually got my R4.g, which is the guy that I'm aggregating over. Okay, so I'm going to show you the process of what goes on for stuff flowing into the in-memory join to answer this particular query. Okay, so what you do is that when a tuple is piped into the in-memory join, I'm going to try to build chains of partial tuples from the left to the right. Okay? So the first thing that happens is that tuples from the leftmost relation that come in are always added. Okay? So no matter what happens, a tuple from that leftmost relation that comes in gets hashed into this hash table. And it's going to get hashed in its R1.a value because you're linking R1.a with R2.b. And so when an R2.b comes in, you've got to be able to probe over to the A table, right, to see if you can build this chain. So everything from R1 immediately goes in, it's hashed over to here. Okay, so then if 5 comes in, and these guys are coming in fully globally randomized order based upon this whole timestamp ordering. Okay, then the 3 comes in. Okay, so now when a tuple from another relation comes in, it's only added if it can join with an existing chain. So in this case, I've got an R2 tuple happens to come in. So it's going to be added if it can join with an existing chain. And now I've got a chain here, and a chain here that I'm building on. And so what you do is you basically say, okay, R2.b, well, you probe this hash table, you find a match, okay, and then the R1 or the R2.c gets hashed over here. Okay, so you've actually got a chain that's going from here over to here. Okay? Yeah.
I don't understand the vertical positioning there.
Oh, this is just a hash table, so this is random.
Okay.
Yeah, so just some data structure. I mean, the hashing isn't important. You could use a tree or whatever. Okay? So now we've got an R3. So R3.d, it gets probed over to here. Let's just say by randomly, this is the hash bucket that it should find a mate in. Doesn't find it, so it gets crossed out. Next, another R3 comes in. It does the probe. It finds something. The 8 gets added. Another R4. Probe misses it. This guy gets killed. R2.b. Oops. I just hit end. By the way, this is all kinds of extra material, so don't think I'm going to subject you to it. It's bad to have the end button right next to the page down. Okay, so I think I was somewhere around here. Okay. Anyway, yeah, so R2.b. Okay. So basically we got this probed right here, and then the 7 got added. Okay. Another R2 comes in, probe, miss. R3, this guy comes in, gets added over there, and now we got 2 8s. And R4 comes in. Here's the interesting one. R4.f probes. Now the R4.g, which is 13, actually gets added over here. Okay? And so now at this point we've actually discovered some tuples that are actually going to produce the result. Okay, are going to contribute to the result. Okay? And so on. Right? So the process at a high level is that a new tuple comes in, timestamp ordering, right? There's going to be some set of links it has. Now in this case it was a simple linear chain, but it can be more complicated. And there can actually be more complicated Boolean predicates going on. But at a high level what happens is a new guy comes in, you probe some hash tables. If you find that he actually adds in, then you hash them to its own thing so you can build these chains up. Whenever a chain makes it all the way to the end, this tote variable is actually updated. Okay? So tote is actually a random variable that again can be statistically characterized. Okay, so using tote for estimation. Yeah.
I know we're going to get back to that. Now, though you mentioned the question of filling up memory.
Okay.
So let's suppose that
Actually, if you don't mind, I'll cut you off right there because you're totally right. You're anticipating something that's coming along.
Okay.
Yeah, so you're right on the ball there. Okay, yeah, so if I don't address that, then ask the question about 2 minutes. Okay, so using tote for estimation, okay? So assume that the recent timestamp, the most recent timestamp of the in-memory join is p, and there are n relations. Okay? So then the probability of this process discovering any output tuple is exactly p to the n over n factorial. Okay? And the n factorial comes into play because you actually discover an output tuple if all the constituents come in first guy first, second guy second, third guy third, and fourth, and so on. Okay? And so that's where the factorial comes in. And this happens because in order, like if you've seen half of each input relation, and there are 4 relations, there's a 1 in 16 chance that you would have seen all the constituents if the sweep line or the p-value is 50% in this case. Okay, so that's the formula. So then an unbiased estimator for the query answer is precisely this right here. Okay, and getting the variance of this thing is actually quite challenging and beyond the scope of this talk. It's actually a very, very interesting question in this case. Okay, but you can get it. Okay, so some additional details. Okay, so note that actually the ordering of the relations matters. Okay, and it's actually quite interesting how it matters. It actually has no effect on the statistical properties of tote. Okay, because that formula that I just showed you, and actually the variance formula, does not change no matter what the ordering. Okay, intuitively it actually might make sense when you think about it, because it doesn't matter if I put this one first, then this one, or this one first, but switch them around, right? There's still a 1 in n factorial chance that I get things in the right order. And there's still a 1 over p to the n, or actually a p to the n chance that I've seen everything. Okay? So the ordering actually does not change the statistical properties of tote. It actually affects the size of the various in-memory joined data structures. Okay? It actually fundamentally affects the size. So why? Well, imagine that we want the average GPA of all people taught by some professor in the University of Florida CS department. Okay? So we're basically doing a join over these 4 tables. So you've got prof, the class they taught, classes that students took, and then the student info. Okay? So what you could have is, this would be one possible ordering. Student, where you append took to it, append class to it, and append prof to it. Or you append class to prof, and then took to class, and student to took. Okay? So here's a quick quiz, see if anyone's paying attention. Which one, the left or the right, would be a bad choice? Yeah, student being first, right? When you think about it, it makes sense, right? Because student is probably a lot bigger. If this is all the students in the university, well, UF is one of the largest universities in the country, 40,000 students, right? This is bad because you look at a student and you don't even know if they're a CS major, so they might contribute to the final result. But prof, okay, our department has like 30 or so professors, right? So you put prof first, and you got a much smaller number here. So you chain in this order, you have a much smaller data structure than if you chain in this order. So this actually requires optimization. Okay, so you have to choose an order. It's actually a very interesting optimization problem, somewhat related to the classic query optimization problem, but actually has quite a different structure for reasons that actually I'm happy to have you ask me about later, but I have to move on.
So it has no effect on variance estimates?
It actually doesn't. Yeah, it's actually quite interesting.
Yeah.
My advisor always used the word interesting to mean painful.
Yeah, well, put it this way, it's actually interesting, so the intuitive reason is interesting, what I just kind of told you a minute ago. But in the end, what you have to do is you have to come up with a formula for the variance, and then you look at the terms and basically say, does this depend on the ordering? And it turns out it doesn't. Okay, so some additional details. So even with a carefully chosen ordering, the in-memory join size can be huge. It can be arbitrarily large. In fact, if the in-memory join discovered all the output tuples, then there would be no reason to do all this, because you would actually be able to answer the query in a single pass. And IBM and Oracle have been doing stupid stuff for 40 years or 30 years now. Okay? So of course you can't do that. Okay? So to deal with this, I didn't mean to say USA, a hard bound. To control, I'm going to use a hard bound and a soft bound on the size in bytes of the in-memory join. So what happens, the way this works, is if the hard bound is ever exceeded, I'm going to choose one relation to subsample so that the in-memory join size does not exceed the soft bound. Okay? So your soft bound might be like, I'm going to give, say, 10 gigs of RAM to this process. Okay? So if my in-memory join ever gets higher than 10 gigs, then what I'm going to do is I'm going to choose one of the relations to take a random subset of, so that the total size of my data structure now falls below my soft bound, which say would be 8 gigs. Okay? So what you do is you subsample that relation, you take a subsample of it, and any chain that is chained off of a tuple that gets removed from that relation gets killed. Okay? So that controls the size. So the in-memory join is actually always shrinking. The in-memory footprint is actually shrinking or actually it grows and then shrinks, grows and then shrinks. Okay? Now, so this subsampling, of course, increases the variance because you're killing information. And so there's another optimization problem here, which is which relation do I get a subsample, okay? And we actually do a greedy thing here where we choose the relation to subsample in such a way that we want to minimize the variance of the resulting estimate, okay? And that's even not as easy as it sounds because you actually have to figure out how much of the relation you would have to subsample in order to get yourself under the soft bound, okay? But then, once you add this thing in, the new unbiased estimator is actually this right here, where you've got this guy where the alpha j is the fraction of the jth input relation that is actually present in the in-memory join, okay? So right now, right, a tuple is going to be in an in-memory join or in the in-memory join if the factorial ordering was correct. That's case one. And the sweep line happened to pass over it. Okay, this timestamp was okay. And it didn't get subsampled out. Okay, and so this formula actually takes care of unbiasing for all those possibilities.
So just kind of make something.
Okay.
So this alpha, you select the alpha, the j that you're going to take as your master in this, with minimizes the variance there.
Mm-hmm.
And that gives you an alpha for that guy. But
Yes.
then you're going to decimate the other ones in accordance to the rule you have for the chains.
Right, right.
And that will give alphas for the others.
Yes.
Is that
Well, actually, no. Actually, everything you said was right until that will give alphas for the others. Okay. So the deal is that if there was like a chain that now is just got killed because it got sliced through the middle. Okay. So now, if the only reason that chain was in there, okay, in particular, like everything that kind of come after it that had been chained onto it, right? If it doesn't have a reason for being there anymore, because what you're essentially saying is, I never saw this tuple. You're pretending like you never saw it. It doesn't affect the sampling fraction for the other relations. But if anything else got chained after it, then this guy right here, this factorial thing, would have never allowed that chain to grow. Okay? So I'm not explaining it very well, but let's say I have R1, R2, R3, and R4. Okay? I decide to subsample R2. There's a tuple from R2 that got killed, where there was an R3 and an R4 couple of tuples that chained after it. What you're effectively saying is, I never saw that R2 tuple. Pretend like I never saw it. Okay? Now, without affecting the subsampling fractions of any other relation, okay, if there was an R3 and an R4 that got chained after this R2, you would have never had that chain in the first place in the in-memory join. So you're basically saying you're pretending I never saw it. So it can be killed and it doesn't affect anything else. Does that? Yeah. Okay. Okay. So very quickly, I guess, providing the timestamp ordering. Okay. So all of this requires some timestamp randomization. It's actually no problem at the bottom level because the data are actually stored in randomized order on disk. And you can actually attach timestamps using samples from a beta distribution plus a little mathematical magic. Okay, so you can simulate in a pseudo-random way those timestamps, not a problem. It's actually more challenging up here, and the reason is that if you actually implement joins as hash joins or sort merge joins, stuff comes out in order that is not random, right? It comes out in the order it wants to come out. And so it actually turns out that you need to modify the operations so that they actually provide for a randomized output ordering. Okay, and providing a timestamp ordering. So, like I said, so most algorithms actually need to be modified to produce at least a semi-random output order. So an example would be a sort merge join. The way you can do this is that rather than sorting R1 on, so actually, let me kind of back up and say, in case you don't know what a sort merge join is. Okay, so this is a standard way to implement these join operations. The way a sort merge join works is that you sort 1, or you sort R1 on the join attributes. You sort R2 on the join attributes using a big external sorting algorithm. Then you do a one-pass merge on the two. Okay? So to randomize, rather than using a lexicographic sort order, which would be the classic way you do it, you instead use a sort order based upon a strong hash of the join attributes. Okay? And so what this gives you then is it actually gives you the sort order or the merge order that you get is actually randomized. Now it turns out it's only semi-randomized because if you join on R1 and R2 on, say, R1.b equals R2.c, you might get something that looks like this. Okay? So this might be actually the order where this is the first and the second and the third and the fourth tuple, right? But here's one more last quiz for you. Why might this not be a great randomized ordering? Or why isn't it perfectly randomized? Actually, I think if you look at it, you actually see that it doesn't look very random. Anyone got an idea what's going to happen with this whole process? If what I do is I basically say, rather than lexicographic sorting and merging, I'm instead going to hash and then sort and merge.
Well, you're going to group them.
Yeah.
And so you know, the order in which they come is not exchangeable at the local level.
Yeah,
You have
exactly.
groups in the merge.
Yes, that's exactly right. That's what's happening, right? So in this case right here, like basically what happens is the merging attributes or the joining attributes come out in clumps. Okay? So inside of a clump, these things are actually indivisible, right? But across clumps, they're actually truly random. And so this is yet another thing that you have to take care of. It actually turns out that this doesn't change, it doesn't induce any bias in the process. Okay? Bias is really it's hard to induce bias in a lot of cases, right? But it's very easy to crank up the variance of something, or at the very least, you actually change the calculations that need to be done. So this is yet another thing that makes the variance calculation even more interesting. Okay, so actually I'll skip over this, but we can handle other types of queries. Okay? And so here is just a very simple example. Okay? And this is actually a bad example. It's old. We do much better now, but anyway. So here's an example of one of the TPCH queries. I forgot which query this is. And so what I've done is, well actually, our system, our prototype system, actually implements this query and runs it to completion in 26 minutes as opposed to 43 minutes on Postgres. So basically we can do all this randomization, all this extra stuff and beat Postgres. Now I want to be really careful because when I give this talk, a lot of people yell at me and they say Postgres stinks, it's not a good system. Why are you crowing about beating Postgres? And that's actually not the point here. Okay? The point is that there's at least some evidence that we're not killing ourselves by doing all this stuff. And I actually have better numbers now that I didn't put in this talk that are more exact. And actually what we've done is we've taken our system DBO and ripped out all the estimation stuff and compared it against itself. Okay? And so on the same query plan, we basically get like a 10% hit. Somewhere in the order of 10% is the price we pay for doing all the randomization and the search. Okay? So that's the point there. But then an interesting thing is that what do our bounds look like? Okay, well in this particular query, like I said, we actually do much better now, but at least in the distant past. What this does is it plots the duration of the query as a function of the bound width. Actually the other way around. The bound width is a function of the duration of the query. So what this means is that I'm guessing the answer to this query. I'm basically saying how wide are the confidence bounds as a fraction of the current estimate. Okay, so you can think of this as being basically what we're saying is we're saying, so at this point right here, after 400 seconds, we're saying that, well, we've got about 10% error at a confidence of 95%. Okay, so there's a 95% chance our error is within plus or minus 5%. Okay, and so we actually get a very nice decline in error. Okay, and so what these lines show is actually shows switchovers in the various level-wise steps. Okay, because this guy has 4 steps that are required, and so here you got a switch and a switch and a switch. And by the way, this guy right here, this axis is logarithmic. Okay, and so actually it's quite interesting that what you see is, it's like I argued before, right? When you switch over a level-wise step, then the information density is much higher, right? And so you actually get a kind of a drastic fall in the bandwidth. Okay? And so the rest of the talk is not going to be used. So are there any questions that didn't get?
I think you got the one that I'd asked.
So how does this estimation work for things that query for exceptions, essentially? So look, sum is sort of I would say an easier example because you're going to have a nice continuous growth or drop off in your error.
Mm-hmm.
But if somebody says, find me some condition where this condition is the max of something or the min of something, or if somebody says, I want to find the top 2% of my customers, you're never going to know the answer until maybe the last tenth of a second or something like that.
Okay, so I agree with some of the things you said and disagree with others. Okay, so actually I could tell you, so there's actually a more, this is probably some of the stuff that you're talking about right there. I mean, there are we actually worry about these kinds of things, okay? Now, max and min in general are very, very difficult because they talk about one tuple, Okay? And we actually have had some success on simple queries by using Bayesian methods. Okay? But because intuitively, the reason is that you can say things about max and min if you have certain prior information about distributions. Okay, so going Bayesian is one solution. Okay, now what I fully admit is that I think at this point, I think we've decided that except in very simple queries, that's never going to happen. So if you're talking max and min, that's the one thing that kills us. Okay, now that being said, okay, if you want something in the top 2%, right? Like let's say I want the sum of all employees or the sum of the salary for all employees who are in the top 2% of our sales force. That is a fundamentally different thing than max or min. The reason is that if an employee generates, say, 10,000 sales per year, okay, even after I've seen a small fraction of the database, right, I might still have enough information to say something statistically about the chance that someone's in the top 2%, right?
Well, true. In a ranking type query, yes. But there are other things where you might want, where the thing that you're computing is dependent on computing the entire set itself. Like, for instance, somebody says, show me the top, let me try to reformulate what I'm trying to say. So if, let's say, the thing that you're computing is based on the sum of everything that you've seen so far. Meaning, somebody says, find me the people who take more than 25% of all the vacation taken by everybody in the company.
Okay.
Right? So for that, you have to compute the average number of days that a person has taken vacation, let's say, for the whole set. And then you would have to find who meets the criteria that you're looking for.
Okay.
So the thing is, the thing I'm getting to is the last filter, the filter that says, yes, this is a tuple that I like or don't like, won't have enough information until it see all the records.
Okay.
Or all their data.
But you'll have you don't
Estimate that on the
you
fly.
can right as you're going through the records you can estimate the amount of the data that you have sampled and therefore the amount of vacation that employees take. So I think you can in that case. I think
But
you can
won't
still
it
do
both
rough
grow
estimates.
in different ways?
So actually, I agree with exactly what you said. Okay. So actually, we can do it, but let me just say that. So what you're talking about is essentially a correlated aggregate query. Okay. And like for example, in the TPCH, there are several of these. Okay. And we think we can handle these. That being said, it's an extremely complex thing. Okay. Because you actually have a cutoff. Exactly what you're talking about. This cutoff, whether or not this guy's in the top 25% or whatever, is actually itself a random variable. And then you have these other things that are not conditioned upon that. And actually, including people or not including people in the final result set, now the inclusion and exclusion is actually correlated with one another because they're actually all conditioned on the same aggregate that itself was a random variable. Okay? And so you actually get all kinds of, now you have to worry about covariances between things and so on. Okay? We actually have a paper, well actually we submitted a paper and plugged some of that stuff in too, and reviews came back and said this is too complicated, take it out. But we've actually worked on that. Okay? Yeah, so it's a great question. I think the take-home message here is that it's a cool problem, right? Because you end up rethinking everything like that, right? And there are only a few things that are really, really impossible to do. And max and min, I think, are in that category.
Great. Thank you.
Thank you. Okay.